Okay, the last that I'm going to go through here with you is NMR, so nuclear magnetic resonance. This one here uses basically radiation to cause the chemical bonds, in this case in carbon, to stretch and bind, stretch and twist and all sorts of things. And what it does is it creates some signals that get detected by our computer and again turns into a graph. And the number of signals tell us how many carbon environments there are. Not how many carbons there are, we use our mass spectroscopy to work that one out, but how many carbon environments. So what I've given up here is an example of propan-2-ol. It's an alcohol that's got 3 carbons. But if we look at this and this, they are simply mirror images of each other. They're what we call the same carbon environment. So if you find a molecule has got symmetry, this is where your maths will come in quite nicely, has got symmetry, and we can see a line of symmetry straight down here. The 2 sides of the CHOH are identical. Then what we've got is, sorry, that's got one too many things on it. Then what we've got is 2 things that are identical. So they only show us one signal on our spectrum. What do we notice about the height of that spectrum, that signal? It's taller. Because there's more of them, you get a taller signal. Okay, so if things are all about the same size, then there's either lots of things with 2 carbons with the same environment, or there's a whole lot that have just got 1. It's not always double the size though, it's sometimes just a bit taller. Alright, and sometimes it's a lot taller. But if it's taller, it gives away that there's probably 2 of those carbon environment. There's 2 carbons with that same environment. They're both bound to exactly the same thing. Then what we do is we find that there is a thing called a shift. Whoops, change colour here. There is a shift that is caused by functional groups. In this case, our OH has caused a shift. So this has affected the size of these carbon-carbon bonds, just subtly, and their strength. And therefore it takes a little bit more or a little bit less, it takes a different amount of radiation to have the same sort of resonant, so double bouncing on a trampoline, the same sort of effect on that chemical bond, because it's been affected by this one. So it shifts what we see here. It shifts it back this way. These are actually large numbers, low numbers. It's a reverse scale. Okay, so 0 is actually here, and this is up in the 200s. So it shifts it this way. Don't ask me why they do it that way, and don't just do the graph the other way. I don't actually know the answer. So a functional group will cause a shift in the signal. And in this case, the OH bond will shift it just a little bit. And again, you're given the numbers on a data sheet so you can match those up. So you can go, oh, that's consistent with a COH shift. So a carbon bound to an oxygen. Sorry, to an OH. Every functional group has a slightly different shift. Some of them do overlap, so you can't use NMR as your only thing to work out what the functional group is. But once you pair it up with infrared, you can be really confident that you've got your functional groups right. Then when you match up the mass spectroscopy, you can confirm that you've got your functional groups right because the fragments would match what you thought. So we would expect to see a fragment of 15 and then the rest of the molecule, for example, in mass spec. So what we're looking for in mass spectroscopy is how many carbon environments. Now if I was to move that OH onto the end here and make it 1 propanol or propan-1-ol, have a look at what happens. There's now no symmetry in this molecule at all. There is no symmetry when we look at the carbons. This is a CH3. So it's going to have its own signal where that one is there. So we'd still get a signal here. I'm just going to go over the top of this one. And it would be lower. It would be smaller because there's only one of them. I'd now have a CH2. This one here is a CH2. So it will be, because it's closer to the OH, will be slightly shifted, but not enough for us to talk about. Be slightly shifted, and it'll be about the same size as the CH3 one because it's also only one carbon. And now my CH2OH would be about where we'd see this one here. And so we'd now have 3 peaks because there's 3 unique carbon environments compared to the 1, 2 that we've got here. And that's our key piece of information we're looking for from NMR. So NMR is about carbon environments, symmetry. So we're looking for symmetry or a lack of symmetry.